We continue with a series of lecture on basic concepts in thermodynamics. In this video, we will be talking about internal energy and, if possible, work and heat. The energy of a system, like we said, is its capacity to do work. And every system has its own internal energy. That's the energy associated with it as a result of its internal motion. We'll talk about that in a bit. And its spatial arrangement. Internal energy, we're giving it the symbol U. In some other places, it's given the symbol E. So it's a state function, and remember, by state function, we mean that it depends on the state variables. For an ideal gas, internal energy is a function of temperature only, but ideally, the U in realistic and a U is a function of state variables, everything present in the state. That also means, as a state function, when there's a change in the states, the value changes. It can be represented by U final, that's the final value, minus the initial value. It is also an extensive property of the system, or extensive variable of the system, because it depends on the amount of substance present. So if you increase, it's directly proportional to the amount of substance present. If you increase the amount of substance present, the internal energy increases. So it varies with the amount of substance present. Well, it's energy, so its unit is kilojoules or calories or whatever it might be. So in the previous video, we said that the ratio of two extensive properties gives an intensive property. So the molar internal energy is internal energy per mole, and we have it is reported as kilojoules per mole. Now, the molar internal energy is an intensive property. It's an intensive property. Okay, so we said that internal energy is associated by virtue of its internal motion. So what is this internal motion that we're referring to? The internal motions are the different motions that are present in the molecule. So we have the translational motion, we have rotational motion, and vibrational motion. A translational motion is a motion in a straight line. Like we said, gases are always in constant motion, and that motion from one place to another is a translational. The translational motion is usually defined with respect to in the frame of the Cartesian coordinate axis x, y, and z. Then we have rotational motion, that is a circular motion about an internal axis. And lastly, we have a vibrational motion, which is a periodic motion or mechanical oscillation about an equilibrium point. So this equilibrium motion, this is an angle bending motion about the angle's equilibrium point. So these types of motions, all these motions, we can call them the motional degree of freedom of the molecule. We know that molecules come in different shapes and sizes and or whatnot. For example, the carbon monoxide is a diatomic molecule, which means it's a molecule that contains only two elements. The carbon dioxide, it contains three atoms all on a straight line. This is another example of a diatomic molecule. It has just two atoms. This contains three atoms all on a straight line. It's a linear molecule. A linear molecule has all its atoms on a straight line. This is another three atom molecule, but this is not on a straight line this time around. It's bent. So once it's not linear, they are referred to as a non-linear molecules. And if it's linear, like the diatomic molecules HF and CO, and also the polyatomic linear molecule CO2, then they are referred to as linear molecules. Now this has a cyclic element to it. Okay, that's an aside. So let's talk more about the internal energy and the degree of freedom. A motional degree of freedom is the way a particle can move. So a particle can translate, it can rotate, and it can vibrate. And recall that the internal energy is as a result of this motion. The motional degree of freedom are related to the kinetic energy, internal energy of the molecule. Monoatomic molecules have just one atom. An example is helium. Most of our group 8 gases are monoatomic molecule. A diatomic molecule has 2 atoms present in it, like we saw in the previous slide. A linear atomic molecule has all the atoms on a straight line, and all other molecules that have more than 2 atoms are called polyatomic molecules. So if they are not on a straight line, they are non-linear polyatomic molecules. Okay, so what's the relationship between this and internal energy? The total number of degree of freedom of any molecule is related to the number of atoms present. So it is given as 3n, and n is the number of atoms present in the molecule. For example, for the helium molecule, n is 1 because it's a monoatomic molecule. So the total number of degrees of freedom is 3n, which is 3 times 1, and that is 3. If we consider a diatomic molecule, n in this case is 2. So diatomic H2, there are 2 hydrogen atoms. HCl is another example. So that's H1 to 2 atoms. So the total number of degrees of freedom is 2 multiplied by 3. That is 6. If it have more than 2 atoms, CH3COH, that's acetic acid. So we have 1, 2, 3, 4. The 3 atoms here, that's 5, 6, 7, 8. So a total number of 3 times 8, that is 24 degrees of freedom. Now this degrees of freedom, we say that it's the way a particle can translate and rotate. They are usually shared between these motional degrees of freedom. And it also provides a crude way of calculating internal energy, and we'll get to that in a bit. So the total degree of freedom is 3n. N is the number of atoms in the molecule. Every molecule, whether it's big, small, monoatomic, polyatomic, every molecule has 3 translational degrees of freedom. There's a summary of it here, and we'll look at them one by one. So for all monoatomic please, 3, every type of molecule that you can imagine has 3 translational degrees of freedom because X, Y, Z coordinate axis. Now, for rotational degrees of freedom, we look at linear molecules. So a linear molecule, all diatomic molecules are linear, and some polyatomic molecules are linear. So for a linear molecule that has all the atoms on a straight line, we looked at a picture some slides back. So a linear molecule has 2 rotational degrees of freedom. A non-linear molecule, so an example is water, has 3 rotational degrees of freedom. And that's because rotation along the internuclear, the axis on the internuclear axis does not produce any energy. Okay. So again, linear molecule, that's a diatomic molecules and some other polyatomic molecules. So once that that means that we have 3 plus 2, that's 5. 3 plus 3 for non-linear. Okay, so before I quickly move ahead, Monoatomic molecules have no rotational degree of freedom. Neither do they have a vibrational degree of freedom. So diatomic and linear molecules therefore have 3n-5 vibrational degrees of freedom. So since there are a total of 3n, 3 of them go to translation, 2 rotation, that's 5 already. The remaining, which is 3n-5, is for vibration. And the non-linear molecules have 3n-6. So then the 6 comes from 3 for translation and 3 for rotation. So the equipartition theorem can be used to calculate internal energy from degrees of freedom in a crude way. So the equipartition theorem states that the energy, in thermal equilibrium, the same average energy is associated with each independent degree of freedom, and our degree of freedom are the translational, rotational, and vibrational. So more specifically, it states that each degree of freedom, quadratic degree of freedom, all of them are quadratic degrees of freedom, but on the average possess an energy of half kT per molecule. So again, because of that, we can use it to estimate the average energy of a system based on the number of degrees of freedom of the system. So let's look at that for a monoatomic molecule, n equals 1, so the total degree of freedom is 3. We have no rotational degree of freedom, no vibrational degree of freedom, and since each degree of freedom contributes to the total, that means that for a monoatomic molecule, the internal energy is 3 times half kT. So that's 3 half kT per molecule, according to the equipartition theorem. And all this is a contribution from translational. For a diatomic molecule, an example is HCl, the total number of atoms in the molecule is 2. So the total degrees of freedom will be 3n, which is 3 times 2, and that gives us 6. The translation is always 3. Every molecule has 3 degrees of translation. Rotation is 2 because it is a linear molecule. All diatomic molecules are linear. And vibrational, the remaining will now be 3n minus 3 plus 2, that's 5. So we have 6 minus 5, that is 1. So diatomic molecules have 3 translational degrees of freedom, 2 rotational, and 1 vibrational. 3 plus 2 plus 1, that's 6, which is 3n. So in trying to calculate the internal energy, usually we ignore the vibrational motion. So ignoring the vibrational motion, so we have 3 plus 2, so 5 degrees of freedom. The vibrational motion is often ignored because vibrational and excited states are not populated at room temperature. Anyway, so the contribution to internal energy from using this equipartition theorem and degree of freedom, so we have 5 from rotation and translation times half kT. So half kT is from equipartition theorem, so that gives 5.5 kT per molecule according to the equipartition theorem. Now this can be extended to other linear polyatomic molecules because all linear polyatomic molecules have 2 rotational degree of freedom. So if we ignore the vibrational degrees of freedom too, we still have 5 degrees of freedom. So the internal energy for a linear polyatomic is also 5 kT per molecule. What about for non-linear molecules? Non-linear molecules have 3 rotational. Let's look at an example. Methane is a good example. N is 5, so the total is 15. Translation is always 3 because it's a non-linear molecule. Rotation is 3. So if we ignore all the vibrational, we have 6 degrees of freedom, and the contribution will now be 6 times half kT. 6 times half is 3, so we have a 3 kT per molecule. So far, for monoatomic molecules, we have 3 half kT. For diatomic molecules, we have 5 half kT.